Hello, everyone. My name's Daniel Cumming. I work for Runtime Verification. I'm a formal verification engineer there, and a lot of what I do is related to Rust and the Rust compiler. And so I thought that I'd share at least a cursory overview about that with you here today. A cursory overview that's going to try to go from start to finish as much as possible. I think that is a somewhat ambitious goal to fit within an hour. It's a pretty complicated piece of software, and I guess trying to squeeze all of the intro details even inside an hour is a bit like trying to fit a school bus into your living room, but we'll try to make it happen. Can everyone see the screen share okay? Can I maybe get some feedback?
Yeah, we can see it, but you might have to move your what is it called? Yeah, just move it up into the upper right corner, I guess, or something.
Oh, you guys can see the overlay?
Yeah.
Oh, nice. Okay. How about that? That's probably reasonable.
That's fine. You won't be able to see any reactions if you put it down there. I don't know. Wait, let me try. Yeah. So just as an FYI.
That's okay. I'll fly blind.
Okay.
Okay. So some stuff that I'm going to talk about today is a basic overview of what Rust as a language is trying to do. This is only going to be brief, like 3 to 5 minutes, just talking about what the language is, which is important because after that, we're going to be talking about the compiler. And the compiler's goal is to take a source programming language that we write in Rust source code. It's going to turn it into a binary. And so it's important to know, like, what is it about Rust that this compiler has to maintain and enforce as it goes through these transitions. And so there's a bunch of things that it's going to need to make sure properties that are held by this source language. And to do that, it will have to do rounds of analysis. And so it's going to transform the language into different intermediate representations in order to perform different analyses at the best points in time that it can. So these 2 points here will take a bit of time, maybe between 20 and 30 minutes, but this is where we're actually going to be looking inside the Rust compiler. After that, I will talk about using callbacks, which is a more interactive way of dealing with the Rust compiler. And these last 2 points, unless I time travel, I don't think I'm going to get to them because I did a bit of a practice run and I had to strip a bunch of content out of here to even just make it towards an hour. But maybe that can be left as a teaser for another day. So let's start off. What is Rust? So Rust, defined by Rustlang group themselves, is a language empowering everyone to build reliable and efficient software. So I think that what they mean by empowering is you get a systems level language that gives you explicit control over your memory allocation, and it's able to compile to many targets, and it's interoperable with other languages through a foreign function interface. So it's pretty powerful. It does a lot. And furthermore, it's efficient. This is able to be compiled down small enough to run on embedded systems, and it doesn't have a garbage collector. And not having a garbage collector is a little interesting because it is reliable without that garbage collector, but its type system is able to give some strong guarantees of memory safety and thread safety. And by memory safety, I mean that the typical foot guns that might be available to you in languages like C, where you're able to control your own memory allocation, like buffer overflow, using after free, dangling pointers, these are prohibited by the type system. So you know if your code compiles that you're not going to run into that error. You also know that there's thread safety in the sense of data race freedom when you do concurrency. This doesn't prohibit you from, I think, logically deadlocking or live locking your code. In that sense, you're thread unsafe, but you are at least free of data races. So all of this is enforced at compile time. And this is done by the fact that Rust has borrowing and lifetime semantics. So the way that it deals with references are that if you have shared data, so this is multiple borrows, multiple references out in the world, that you are unable to mutate them. So you know that if you have shared data, you can't change the data. You also know that if you have mutable data, you're unable to alias it. So you can't make two references to it, two mutable borrowers. And through making sure that these are all enforced at compile time is how they get those strong guarantees. As with anything, though, there are some caveats. So the memory safety and thread safety comes with the assumption that you haven't inappropriately used the unsafe keyword. Using the unsafe keyword gives you a lot more power to directly manipulate things like memory and raw pointers, but it then also empowers you with the foot guns of getting all of the memory bugs back in. So on the flip side of that, you are also able to safely mutate shared data and alias mutable data with the appropriate use of the unsafe keyword. So if you use it appropriately, you can do these things and be empowered. And so a good way to do that would be to use the standard library, which is essentially wrapping unsafe code to give you things like vectors and atomic references for concurrency. So there are canonical ways to use unsafe code in a reasonable way. So that's what's going on with the language of Rust. And so now moving on to Rustc. Rustc is, as I mentioned, the program that's going to take the Rust source language down to a target binary. And we'll have a look at the GitHub for that here. So this is the Rust compiler GitHub, and maybe I'll bump that up in case it's a bit hard for people to see. Also, feel free to turn off the mic and interrupt me at any time. I love questions and interjections. They fuel me. But here, maybe I'll point out there's 4 interesting directories. I'll do a bit of orientation because when you first get to this GitHub, it can be a little overwhelming. Tests is all of your test code, so there's not too much that we'll need to talk about in there today. The source directory is not relevant to the conversations that we're having today. There's a bunch of stuff with documentation and other things auxiliary to the point of this talk. And then there's compiler and library. So compiler is where most of the code that we're going to interact with today exists. And that also does rely on the library code existing. So I'll take a look in these in a moment. If you clone this compiler and build it, there'll be a 4th directory called build, and that will contain the actual Rustc binary that you can run. It takes a long time to build, and it does use up quite a bit of space to do it. But if you want to do it, you're more than able to. In order to do it, you will need to use the scripts down here, which are the X scripts. So there's x.py and x. X.py allows you to have some configuration, maybe stuff that we'll be able to touch on later. But if you do that, it will put some compilers in your build directory. And when I say compilers, that's because the Rust compiler is a bootstrap compiler, meaning that it is the code to write the compiler for Rust is itself written in Rust. So if we take a look in one of these many, many crates here that make up the compiler itself, we'll choose here. In here, we see that this is all Rust code. So this is code that makes up Rustc, and it itself is written in Rust, which might be a bit confusing to some people if you're unfamiliar with bootstrapping. But it's pretty clever compiler design, and I encourage you to look into it if you would be interested. So inside the compiler directory, we have many, many crates. And so these crates are responsible from everything from going from the binary, the source language down to the binary and performing all the analyses on the way. all of this is going to be happening at different stages along here. When I first started writing this talk, I thought that I might actually go around through these directories, but
Wait, sorry, we have a in the chat. Could you check that really quick?
Sweet. To build a compiler using language itself, the C compiler is also built in C. I don't think that this is a rule. Like, you can build compilers in external languages, and in fact, there's a lot of frameworks. Like, you can use Java Cup, and I think it's called Flex YYC. These are all frameworks for how to build compilers and parsers for a grammar that you can define on the spot. So it isn't a particular rule, but it is. I think there are many different Bootstrap compilers, and there's definitely a lot of benefits that people have to doing their own bootstrapping. What compiles Rust into a binary? So that would be the Rustc program. So when you typically, if you're experienced with using surface language Rust, you might have used a tool called Cargo. I don't know if you can see this that's being shared on the screen, but Cargo is your sort of canonical way of interacting with the Rust compiler. But when you do a Cargo run, what this is actually doing under the hood for you is it's running Rustc. And it does it with a bunch of arguments to make things easier for you so that you don't have to worry about that. But Rustc here is the program that is going to take the binary, the source language down into a binary. And so back over here, this GitHub is the GitHub that contains all of the source code that will give us that Rustc binary if we build it. Now, it's also worth mentioning that there are a couple of different versions of the compiler. So when I was back here, if you had a scene when I did Rustc version, it comes up with the word nightly here. And this is because on this repo, there are nightly pushes to the Rust compiler, like as in every single night, with changes. So this is all sorts of different activity coming from the community to try and improve the compiler, add new features, clean things up, fix bugs. But people generally want something that's a bit more stable. And so there are also stable releases of the compiler, which are more reliable, and they're excluding more of the experimental features. So aside from the stuff that's in this compiler directory, there's also the library directory, and this is containing a lot of the primitives that exist in the language. Things like the core library, and here you have sort of the core types and things like pointers, that sort of stuff. Things to do with all your types and handling panics and all that kind of thing. And in here, in allocation, there's all stuff to do with allocation, and there's the standard library down the bottom. So this has things like vectors and slices and all stuff that if you're familiar with using Rust, things like print line, these types of macro functions are inside the standard crate here. So all of this is in some way useful when building the compiler. This directory will depend on some things inside here. Getting back to the slides. So I mentioned the bootstrapping and the nightly releases. If you are at all wanting to interact with the community and get involved in learning more about the Rust compiler, there is a Zulip. It's a fantastic place to go ask questions. I encourage everyone that would be interested to go there. So that's the GitHub for the compiler that has all of the source code, but this is trying to implement an idea. And the idea is, of course, going from the source code down to the binary. And so this is my illustration of all of the things that we need to go through in order to achieve that goal. So at the top level up here, I break the process down into three main stages. There's the Rust source code level, there's the Rust intermediate representation level, and finally we have code generation. And so each one of these inner boxes is a different representation of the code on that way. And some of these dot points are different things that we have to do to the code to get it into the format that we would like. And there's different rounds of analysis here in order to make sure that the code is well formed and conforming to what it is that that language promises to do. So I'll start going down through here, and I'll use a hello world example as a motivating example for us to view some of the different forms. So if you're familiar with Rust, this is pretty much as simple a program as you can get. You define the main function and you tell it to print out hello world. So Rustc, when it sees this source code, the first thing that it's going to do is decide that it has to transfer this into its next form, which is an abstract syntax tree. But on the way to getting there, it has to do a few rounds of analysis that I'll point out. So I'm aware that some people might not be familiar with compiler terms here, so I've added some definitions. But an abstract syntax tree is a tree, like a tree is in a graph tree, representation of a source program. And so to get the tree, we need to go through two things, and that's called lexing and parsing. So lexing is where we take in a stream of characters and we're going to read them in and choose, or not choose, but we recognize tokens that they match in the language. So up here, we see fn and then some white space, and we know that this is the start of the declaration of a function. So this is the function definer, and seeing this string of characters before either white space or the open parentheses means this is the identifier of the function name. And so lexing is to take in all of those tokens, and once we've done that, we parse them into the tree. This is where we take those tokens and put them into the tree. What that looks like when I say tree, to give you a graphical idea from the Wikipedia, is this is what an abstract syntax tree looks like. And this is representing a simple program where there's some statements, a sequence of statements. One of them is a while, and a while has a condition and a body. This condition is the comparison of a variable with a constant. And if you go into the body, there is a branch. In that branch, there's a condition that's going to compare two variables, A and B, and it has an if and an else, both of these being assignments. So this tree is a way of representing a program that is useful for compilers. And so the first thing that Rust is going to do is try to get there. So it lexes and parses to get into the AST. However, it then, to get all the way down, it needs to expand macros and name resolution. So, or expanding the macros at least. But we can view, that's why I put some white space here, we can view what that unexpanded program looks like. So over here, I have our hello world example, and there's a bunch of commands that I've written down that you can run from Rustc in order to view different points of what's going on inside the compiler on the way. So here, this command is using the -z flag on pretty. These flags are not necessarily easy to find, but if you use Rustc help, what it will tell you is if you want to know some stuff about the compiler, there are some unstable options that you can find with -z help. So Rustc -z help will spit out a whole bunch of -z compiler flags. And using these, you're able to sort of tell it to dump out information about the state or turn off certain things for the compiler, depending on what you're interested in, which could be a whole range of different things. So if we wanted to know some stuff about the AST, we might go Rustc -z help, and then we could grep for the AST, and it will tell us here a bunch of flags: AST tree, comma expanded. And so these are two things that we can provide to the unpretty flag in order for it to dump some state for us to look at. So having a look at, I've already run both of these commands, and we'll have a look at what an abstract syntax tree looks like when Rust is dumping it out. So it doesn't look like that graphical representation where you have nodes and arrows pointing to the nodes. Instead, it's like a comp style math graph where you have nodes, and then part of the node will have a pointer or indicate what it points to next, a label. And so this AST here is corresponding to this program. If I split it to the right, although it looks quite different, but this is the first thing that the Rust compiler has done to try and turn this into the binary. Is it's taken this hello world program, it started at the crate level, it's created some idea of there being some items. We can see a main function exists here, which makes sense. It is indeed of a kind function. And inside here, I know this is hard to read, we won't spend a lot of time digging into it, but inside here we can find a call to the print line, and we can also find our string literal hello world. So all of this information is in here, it's just been expanded into a graph. If we want to see so as we saw in there was still the print line as a macro, but this ends up getting expanded straight away. We can use the Rust analyzer to predict what this will get expanded into by using the command expand recursively at the macro. And we can see that this print line function will get expanded into the standard library IO module or crate underscore print function.
Sorry, so a VS Code plugin you use for that, or is that?
Yeah, it absolutely is. So if you are wanting to do stuff with Rust, I almost certainly encourage you to use the Rust analyzer. It's I thought it would tell me how many people used it there, but it's got 4 million people that are using it. This is part of the Rustlang team, and it's using an LSP to give you a bunch of information in the IDE. It's very, very helpful for using Rust. And so one of the things that it can do, amongst many other things, is expand macros.
All right, we have another question in the chat, sorry.
Yep, go ahead. Could you read it out to me if possible?
Sure. Why or when would someone ever want to see the AST of their program? Is this tool mostly for people who want to work on the compiler?
It is. It is mostly for people who are interested in compilers going through the AST, but it's not exclusively for that. So if you are interested in compilers, going through these different stages is important. But for us, we need to understand what's going on for these intermediate representations at runtime verification, because we would like to build tooling on top of it. So we want to be able to do theorem proving, deductive verification, and build our own interpreters for Rust. And we can't just do this at the source language level. We end up needing to have some more low-level representation. And so we're going further down to something called the middle intermediate representation, but there are many other programs that are working with intermediate representations of the Rust compiler for their own business case that they have. Although I will admit that generally people looking at this are people that are looking at compiler or interested in the Rust compiler itself.
Okay, another question came in. I have a question related to AST. Rust have macros that allow you to generate code. Are these related? I think the question is asking the relationship between AST and the macros.
There is, in the sense that the AST that I showed you before has them unexpanded. However, and then there is the ability to expand them. So this tree ends up being a lot larger because all of these macros have been expanded. But the existence of an AST isn't dependent on a macro in that sense. They are like mutually exclusive. Or I shouldn't say that actually, because the macro must exist in the AST. But those ideas are related in that way. But when you do create a macro, you do. So if the question is related to when you write a procedural macro in Rust, it is true that you have to think about lexing and parsing tokens at that point, which actually probably is what the question meant, is someone who has looked at that. So you do have to think about this sort of stuff when you're working at the surface language level for those macros.
Okay, I got in the chat that answers the question. Thank you.
Nice. So this is, I mean, obviously we can take a look at all this stuff all day, and I know that everyone attending would be thrilled to do so. But we'll move on. So this is the abstract syntax tree. And another reason why we might want to be looking at this stuff is we might want to debug a program that's particularly nefarious, and we have some knowledge of compiler stuff, and we want to see what actually is getting spat out. So the next thing after the AST that we need to do is we want to transform that AST into something that that's very similar to it, but is more amenable for us doing analysis to. And so this is going to be the high intermediate representation. In order to get there, we need to do some lowering and desugaring. And what that means is features of the Rust language that do the same thing, we want to streamline all of those into one representation. So in Rust, you can have for loops, while loops, and the infinite loop, just the loop keyword, and break or return inside it to exit that loop. And all of these three things are ways to have a loop. But here wants to get rid of the multiple representations, and it just works with the loop keyword. And so a bunch of different features that do the same thing, it streamlines them into one. Control flow all gets turned into match statements, I'm pretty sure. And that's lowering and desugaring. Once we have done that, we're now inside a here representation, and we can do our first rounds of analysis, which are type inference, trait solving, and type checking. So this is starting to get to that idea of like what the Rust compiler is guaranteed. It guarantees you a type safe program, but on top of that, it has a lot of other things. So I'll show roughly using some commands here. We can do the same thing. We can dump unpretty here and unpretty here tree. We won't need to spend much time looking at this. This first here one almost looks identical to the original program that we started with. So on the left here, we have our original hello world in the surface language. And the here at this point has added in the prelude. It's added in that we're using the standard library, things that we are able to elide and we don't have to mention at the surface language start to be made explicit. And here we can see that the macros have been expanded, and the actual construction of this string into a constant is a bit more explicit. There's also the here tree output. And so this is really what's more so happening inside the Rust compiler. It gives you a less pretty printed view. And so this is almost the same as the AST. It looks very similar, except there are some other things going on which are really, really important for the compiler to be able to do its analysis. It starts allocating these things called def IDs to everything that has a body or is something that can be alloced. And every single expression that exists inside the code is given a here ID. And these def IDs are not just useful at the here level. They're going to get carried down through many rounds of analysis as identifiers to different points of things of interest in the code.
Sorry, what do you mean when you say getting alloced? What's that mean in this context?
What I meant by an alloc is things that exist at some point in memory. So that might be a global, that might be an, you can also alloc consts. But there are this idea of things that end up getting allocated in memory. And yeah, that's what I meant by that. So that's the here representation. And when we want to do rounds of analysis, there are some things to, I guess, for the interest of, learning about this. At the here level, the things that we do for analysis are trait solving, type inference, and what's the last thing that we do? We do type checking. So an example of type inference here is the fact that this V, I haven't actually explicitly told it that this is a vector of strings. Now, the Rust analyzer has in gray told me, like, I know that this is a vector of strings, and how it knows that is because it's using the information from the Rust compiler to do type inference. And it knows from the context of what's happening here that it must be a vector of strings. So that's type inference. And trait resolution is, or trait solving is the Rust compiler deciding that for the generics that I've used, have I used generics in a way where it's possible to actually construct functions that will be able to have the concrete instantiation for what I've asked of them. And so that was very wordy, I know, but my example for that here is I want to log some elements. I have a function log elements, and this is a generic function of a vector of t. What I do inside log elements is I enumerate every element, and I, for my test here, I just print out the index and the element. But the print line function says you can only print an element in the way that I've done it if it implements display. And so here I've had to put a trait bound on display, a trait bound on t, where I've said t, which is generic, it can be anything, except it can't be something that doesn't have display. I know that one thing that must be true of t is it has to have display. And then this function will resolve. If I take this away, the Rust compiler will say, I can't solve for these traits. You're asking me to create or to satisfy a trait bound, and I don't have the ability to enforce this. It's too weak. So that's what trait solving is happening, and it happens at the here level as well. And then type checking is something that we're probably all familiar with. I'm sure everyone here has written a Rust program or any kind of program and they've got the types wrong. Like here, you can't assign negative numbers to a U32 because it's meant to be unsigned. And so there's a lot more that goes on with type checking. Type checking is much more complicated than just making sure you don't put the negative number in the the unsigned one. But that's an example of going through and making sure type checking is satisfied. I might go back. Whoop. All right. So any more questions? Jeffrey?
No, that's pretty clear.
Cool. So this is all happening at this stage. We're getting about halfway down in our representations. So we're still, this here, it still looks like an abstract syntax tree, like where we came from, but it has a little more information to allow us to do our analysis. The next thing that we want to do is transfer that here into THERE, typed high intermediate representation. And this isn't that different to the here. It just, everything has been type checked and all of the types are completely elaborated. I'm less familiar with this than everything. I did a little bit of Googling, admittedly, to see what is the THERE actually used for. And from what I can see, it's used to, the analysis that's done on the THERE is things like unsafety checks. So if you're using the unsafe keyword or you're using different functions that rely on unsafe, it will wait until it's got the THERE to check if you're breaking any of the rules around unsafety. Just quickly, and I mean very quickly because it is completely unreadable, in my opinion at least, when I had a look at it for the first time today. But you can use Rustc-z unpretty THERE tree, and you can use unpretty THERE flat to have a look at some extremely massive graphs that I'm sure there's lots of information if you're someone that's familiar with reading this stuff in there, and there's a flattened version of it here. This is a look into what this looks like, but the important thing is it's used for rounds of analysis, this one for unsafety. So this is still an abstract syntax tree looking form, but the next one that we go to from THERE to MIR, this is where things change up. So now we change from an AST to a
before we transition, there's another question here.
Yeah.
Checking my understanding here, but we can create tools like Rust Analyzer using the compiler artifacts provided by the Rust compiler, for example, HIR, AST, etc.
Yeah, so I must admit, I'm not entirely booked up on how the Rust Analyzer is doing what it does, but the LSP that it has, the language server protocol, is in some way aware. I don't know, it must be referencing this source code directly, and it's able to, on the fly, ensure some things about this process, if not maybe everything at some particular levels are holding. But it isn't compiling your code and creating an artifact in the target directory when the Rust Analyzer is running, but the things that it's telling you are things related to making sure you have a valid AST, whether or not you're breaking type inference, whether or not you're breaking your trait bounds. Like it can show you the type inference, it can tell you when you've type checked wrong. So all this is coming from the Rust Analyzer. So it is definitely related to this. The exact relationship with I haven't dug into myself. Any more questions?
Nope.
Cool. So once we're or to get to the MIR, we're going to need to change the AST format into a CFG format. And so CFG stands for control flow graph. I thought I'd look up a graphical representation for that as well. And to my delight, when I went to the Wikipedia and I clicked on the picture, it actually shows you a Rust MIR program as the example. So this is a better view than, at least if you want to see what a CFG is in terms of like actually seeing the blocks and the arrows. But this is some sort of Rust mir program. It's at the mir level. And what you can think of is there's a bunch of information declaring some places in memory, which are going to have some type. So this is just, these places in memory are going to be assigned something at some point. And then the actual program is here inside these nodes of the graphs, with these being the edges of the CFG. And here, basic block 0 has a list of statements. These statements are performing assignments to those places in memory. And then it gets down to a terminator, and this terminator makes some decision. It's going to do a switch based on some int, and it either takes this branch or it takes this branch to go to basic block 1 or basic block 2. In basic block 1, there's 2 assignment statements, and then basic block 1 always has an edge to basic block 4. Basic block 4 has a few statements and it returns. So this is the graphical representation of what a CFG looks like. So this is different to what our AST looked like. Also, these can point back around in loops, like that it would be reasonable for 2 to branch and wrap back around into 1. That would be a valid CFG. Oops, where am I going? Oh, back here. And so once we've transformed the AST into this CFG, and why we would want to do that is because it's really beneficial for the next rounds of analysis that we want to do. Here, the rounds of analysis with the mir are the drop elaboration and the borrow checking. And so what you can think of is this is kind of that Rust memory safety guarantee that I spoke of right at the start of the talk. This is where this is getting enforced. All of the borrows, all of the lifetime, making sure that all of the memory allocation is handled correctly with allocation freeing, all of that stuff. All of that analysis is happening at this level here in something called the borrow checker. And so mir has a really nice, so if you remember, this is our hello world example. Mir has a really nice pretty print option that's useful to get a flavor for what's going on, that you can use with unpretty mir, but a nicer option is to use unpretty mir, and you use this flag here where you do a minus promote temps that turns constant promotion off. So constant promotion isn't relevant for what we're trying to look at here. That's why I turned it off. And so if we put that one to the right and we take a look at this. So on the left, we have our hello world source example, and on the right, we have our mir representation of it. We do get a warning straight away that this is a pretty printed version of this. All bets are off if you're going to take this a little too literally. And what we can see is, just like before, there's a bunch of declaration of places in memory where with our CFG, we're now in this idea of we don't have variables, we have places in memory, and they have some types. Place 0 here is always reserved for the return of a function. And the rest of these you can think of as like registers, if you will, or just, literally places in memory. So this function here prints hello world. The way that it does that through a control flow graph is it starts always with basic block 0, and it assigns to place 4 the constant string hello world. It then creates another place in memory, which is a non-mutable reference to that constant of hello world, and then it tries to create whatever an argument's new const is of 3, which was the reference to hello world. If that succeeds, we're going to branch to B1, and if that fails, we unwind, which is like aborting the program, but literally unwinding up the stack all the way back, the call stack. B1 here is going to assign to place 1 in memory, the output of printing what was in 2. And what was in 2 came from basic block 0, which was the constant hello world. So we're going to literally print hello world. If that doesn't error, we're going to, the terminator here is going to take us to basic block 2, and otherwise we unwind back up the stack, and basic block 2 just returns. Because the return type here is the unit, it returns nothing. So that's like a crash course on how to read a Mir program. As I said, Mir is doing a lot of those memory guarantees like lifetimes and borrow checking. So after all this, we're finished with the Rust intermediate representations. And the last thing that's left is code generation. Code generation is something I'm going to breeze over pretty quickly. But what's important is what generally ships with Rust is LLVM IR. But this section here is actually really, you can change it. You can exchange it with other really common Codegen backends like GCC, CraneLift, but you can also write your own custom Codegen backend. Maybe you have a particular use case for turning Rust after these rounds of analysis have happened at Mir, and you say, okay, but now that I've got that, there's a whole bunch of different code generation from what everyone else in the world is doing that is useful for my particular business case. An example of this is the Carney model checker, which takes, I think, all of this and then uses some interesting code generation for, I think it's CBMC or something like this, to do model checking of programs. In order to get from Mir to LLVM IR, you have to go through quite a lot of different stages. Constant evaluation, so all constants in a program that you write in Rust are evaluated before you even get to code generation. It's done, well, yeah, it's evaluated every constant that it can at least. And as well as that, you do even more lowering. If you remember, lowering was sort of normalizing what was going on. And the lowering that is happening here is called single static assignment. This is a big simplification as well. There's a lot more that goes on. And then another thing of interest is there's monomorphization. So when we write in a powerful language like Rust, we have a lot of generics. We want functions to be able to take multiple types, and we want them to be able to return multiple types. We want traits and all this stuff. But when we get down to a binary doesn't really understand what any of that stuff is. Instead, there's a list of different functions, and as the program counter is stepping through these instructions, it's jumping to different points, and the binary itself doesn't understand a generic function. And so the monomorphization is taking all of the possible generics that can be satisfied and creating individual functions in the code generation of the actual assembly, or LLVMIR in this case, so that you can handle all the different types you need to for your generic code. Once you're in LLVMIR, there's a ton of rounds of optimization, and LLVMIR is getting pretty close to a binary representation at this point. Using the commands, I was able to admit it using LLVMIR and LLVMVC. That's this one here. And LLVMIR is, well, I want to say this is readable, but I have no idea how to read it. But I did notice that I could see hello world in there. But I haven't spent any time in my life really going through LLVM. I can see that there's loads and stores. But if you don't like that, you can also use the LLVMVC, which is, you know, if that's your kind of thing, that's good too. But that after LLVMVC, after LLVMIR, there's only one more place to go, and that's to the actual binary. And so the actual binary is the target of what it is. So whatever you're compiling for. So this machine that I'm running it on runs on x86, but you might compile to WASM, ARM, whatever. This is probably the path that if you've used cargo before that or at least this is the end that you're familiar with. You've written a Rust source program up the top, and then you say cargo build, and it spits out at the end a target. But this is everything that happens on that journey. You can get a bit of a view into the assembly of it, like without looking directly at the binary, using emit ASM. And so, as I mentioned, my machine's an x86 machine, and so this is the Hello World program as x86 assembly instructions, which, you know, if you've looked at x86 before, this might be somewhat interesting. I don't know. I know that you can do debugging at this level, and I assume on every level up above. So that's it for the round trip of what's going on with these particular IRs. That's start to finish. So I am aware that I'm pretty close to time. What did you want to do, Jeffrey?
Maybe what we should do is, maybe what I can do is just collect everyone's emails and we'll invite everyone to a part 2. Would that be?
Yeah, sure. I mean, I've got all the stuff here to sort of show a bit more interaction, but maybe that's actually a good place to cut off. That's a walk through the different IRs and how to examine them. Still, if anyone would like to ask any questions, I'm happy to stay until the last ones are gone.
Oh, so you have actually have another question here.
Abstract syntax tree to Rust is like application binary interface to Solidity. The application binary interface. So if I understand correctly, and I'm not saying that I do, the ABI is like, it contains all of the actual Solidity, the EVM bytecode, and it contains all of the information for how to access it as well. Like what are the handles into it? Maybe actually, Jeffrey, you probably know more about this than me.
Yeah, that's right. Yeah, that's correct.
Yeah. No, I wouldn't say that that's what the AST is. The AST is actually really just showing you what the source program was in Rust. So showing you function main, open parentheses, close parentheses, open curly brace, but it's done it in a way where it's all of those are a node in a graph, and it has some way of determining already at that point whether you're parsing a valid program. So if you write instead of function main close parentheses and open parentheses, you won't be able to create the abstract syntax tree because you've already broken the rule when you've started parsing. So the ABI is a bit further advanced down the path. So Solidity would have to create its own abstract syntax tree when it's initially reading in everything that is in the source language, all of the characters. ABI just contains the function that, yeah. Nice. The Rust compiler itself doesn't generate any binary code. That's the job of Yeah, actually, that is true. The code generation, that part that's at the bottom, so whether that's LLVM, GCC, or whatever, that's going to handle the target. So you choose a target, whether that's x86, ARM, or whatever, and so that's your binary, that's your target. And it's the job of the code generation to do that. So I mean, I didn't probably fairly, like I mentioned that like that's a different IR to here. It's, you know, separated, but really the code generation is in large part inside the Rust compiler itself. But I didn't really consider that as an IR itself because it's so replaceable, and you can bring in your own custom one from outside completely, but you can't do that with the Rust IRs, and so that's why I separated them. So going back to this, what we did last time was we looked at all the IRs. So those are these little boxes inside of the dotted ones. The dotted ones are my way of representing. So this is the source code. These are some intermediate representations that are still in the Rust environment. And then there's code generation. And the code generation is, it's kind of separate from the intermediate representations in some way. Now, from the source language, you go down to an abstract syntax tree. So this hasn't really modified anything from the program or done any analysis. It's just simply taken all of the text that's come in, like as characters, a stream of characters, and it said, let's group these into a tree structure because we're going to prefer a tree structure to do some analysis later. And so we turn it into an AST by lexing and parsing. It's still got the macros in it at that point, so we want to expand the macros. We want to fully elaborate the names to know where everything is concretely, all the way down to the crate root. And once we have that, we have the AST. The AST is then massaged a bit by lowering into the higher intermediate representation. And this is the first intermediate representation where we can do our rounds of analysis. So from here, we can do the compiler does like its first pass of guarantees, and that's making sure that all the types are right. It infers some of the types that you didn't explicitly put in there, and it will make sure that the bounds that you have on all the traits and generics that you've started doing are actually possible to be instantiated. So that's called trait solving. So once all the type checking's done, there's a little more desugaring, and you get to typed high intermediate representation. And so this is all of the types are fully elaborated. And I don't know much about this, but I do know that unsafety stuff is checked here. And this is our last representation as an abstract syntax tree. From here, we go to the MIR, middle intermediate representation. And so we transform from an abstract syntax tree to a control flow graph. The control flow graph being a sequence of basic blocks where we have statements inside those basic blocks, which are not talking about variables anymore. They're talking about assignments to places in memory. And after you go through a sequence of statements, you get to a terminator, and the terminator will potentially branch, and it can point to more basic blocks. And this is now the layout of the program. So there's basic block 0 where you enter, and it can fork and go to different basic blocks, and eventually we'll get to the final basic block and terminate. So this intermediate representation is where we do the analysis that ensures that all the borrowing and the lifetimes are sound. So making sure that that shared data is not mutated. So so there can be multiple references out there to shared data, and it's going to make sure that none of those references are mutating that data. And it also makes sure that if you have a mutable reference to that data, then anytime someone tries to create an alias to it, it blocks it. And so this representation is where all of that work is done to give those guarantees. From there, we can go to code generation. There's a little more massaging that needs to happen here. Also, before you get to that, you need to evaluate all of the constants. All of the constants are checked out, or all the ones that are at least evaluated, I believe, get done at that point. And then you need to process all of the generics out. So all of the generics become concrete instantiations of whatever functions are going to be called with concrete arguments. And all of this is done to get into in this example, LLVM IR, but as I mentioned here, there are different options. It doesn't have to be LLVM, but whatever the code generation representation is, we get to that point, and then we go down to our target binary. Oops. And that's just if you're used to just doing cargo build, that's where you start at this level, and then you do build, and it comes down, and you have your binary down the bottom here. So normally you skip looking at all these steps, but we had a bit of a look at them. So what I want to move on to now that we've sort of talked about these IRs is it'd be really nice if instead of just dumping them like we did, where it just at some point during the compilation, it just spat out a string representation, a pretty printed representation of what they were. It'd be nice to be able to actually, while the program is running, say, hey, I want the compiler to pause now, and I want to have a look at that representation. And I also might want to write a program which is going to do some analysis or some manipulation to that data. There might be things I need to know, and you can write complex programs that look at it. So the key to doing this is that Rust allows you to call the Rust compiler through bringing in a crate inside itself. And this is the Rustc driver module. So when I gave this talk at Rust Brisbane, I think that there was a little bit of trouble when I said that briefly. So I'll do a bit of stressing over this point because it might be a little bit of an elusive one. But you can write a Rust program here. This is just the main function. It's a bit pseudocodey, like I'm just doing the ellipses there for the arguments. But this program, this main function, will look at an internal Rustc crate called the driver, and in there, it can create a new instance of the compiler and run it. So this whole program is going to get compiled by Rustc, and then when you run that binary is going to again call a new version of the Rust compiler. We're going to point it at some Rust program here and compile it. And the reason why we would be interested in doing this nested compilation is this Rustc driver compiler, we have the ability to pause that compilation and manipulate the IRs there. And we can write complicated Rust programs, in the lines previous to this when we pause it to be able to do analysis and manipulation to it. So if you want to do this type of thing, there's a couple of steps. So the paradigm to bring it in is you write extern create Rustc driver in your Rust program, and you also have to add a feature flag that I'll show in the actual source, but this is the crate to bring in to do this type of thing. But you need a little bit more than that. If you just do that and you try to run it, Rustc is going to barf and say, I don't have all the things I need to be able to do this. And if you're using Rustc, which I certainly recommend you use, you can just, it will give you this command on the command line. It'll say, hey, I need to install some more components. These are the ones I need to do what you're doing. So I guess first I'll just point out where you can find this. So if you recall from us talking, this is the Rust crate, and in there, most of the code that we care about for this type of talk is in the compiler. And in here, there's two crates. There's the Rustc driver and the Rustc driver impl. These are the crates that I'm referring to here. I think driver just points to the driver impl, but in here, this is where the code is that we're going to be leveraging to do the nested call on the compiler. So what that looks like is this. So this is what I would consider the minimum example for running the compiler. Jeffrey, you maybe give me some feedback. Do I need to bump up the font size or anything like that?
It looks fine to me, but it probably wouldn't hurt. It seems like you have enough space on the right side unless you're going to use it later.
No worries.
Yeah,
cool. So here, maybe before we look at this source code, I'll bring up that inside this source directory, there is only this main.rs file, but something that I have external is this hello world saying hello RareSkills. But this is actually outside of the source repository. And if I hover over this, it says this file isn't included in any crates. So this is not going to be involved when I do cargo build or anything like that. It's separate, but I am going to point to it later. I just want to point out now, it's not part of the package. So this minimum example of using the driver is a little bit simple. We're not going to do any interruption of the callbacks. We're just going to run the compiler from inside a compiled program. And to do that, we bring in the crate Rustc driver. If we're going to do that, we need to add this feature flag saying that we're using Rustc private. And then as long as we've added the components, everything's all good. The first thing that I'm going to do is I'm going to take some arguments over the command line, and that's where I'm going to point to this hello world program. And what this Rustc driver compiler needs to take are the arguments, what you want to point it at, and it takes those callbacks. Like I said, the whole point of this is to be able to interrupt the compiler, but we don't want to interrupt it at the moment. So all I did is I just made an empty struct callbacks. Oops. I made an empty struct callbacks, and I implemented the necessary trait in order to be an argument for here. But I haven't done any changes. It's just, it doesn't have any overriding of the functions in here. It's an empty block. So this is just going to be the default callbacks, which, as it turns out, just do nothing. They just let everything pass. It just calls the compiler. So what we're expecting, if I do, I guess what I'll show first actually is if I cargo build, I shouldn't end up with anything happening, but I'm going to build this main program. So cargo build, and I now have in my target here a binary, which if I run the binary is going to call the Rust compiler. So I can run that with cargo run, and if I add an argument of hello.rs, hello RareSkills, what we're expecting is we'll come into this main function. We're going to grab the path to this Rust function here, which I called build before, and no binary got built for this external source code here. And then it's going to run the compiler. So I should be expecting a binary to be output. In fact, I can show that it's going to call the Rust compiler by not pointing it at the program. And it just prints out the help message for Rustc. And it's telling me, like, you're doing wrong usage. If you're going to call Rustc, you need to give me an input. So that's annoying me. So if I do that again, but I add an argument this time, pointing at that, we should expect it to build a binary that's going to print out hello RareSkills. And it does build a binary, and if I run it, it says hello RareSkills. So hopefully that's pretty simple. We haven't done anything too crazy at the moment, but hopefully the idea that we're doing a nested call to the compiler is clear. So I'll remove that binary, and actually first I'll go over. So let's have a look at what that trait is that I was calling inside the actual Rust compiler here. So I guess probably kick it up a bit. So if we come inside Rustc driver impl source lib, and we have a look, eventually we're going to see the, here we go. We're going to see the callbacks trait. So this trait here, you can have a config function, but there's 3 other functions which are interesting to us. There's after create root parsing, which I did notice when I had a bit of a look at this before. It looks like this is deprecated, but I think it still works at the moment. But after create root parsing, it takes a interface to the compiler and a queries. And what you can do is add inside the body of this function, if you override it, some your own custom code to look through the query system at what's happening inside the compiler at that time. And then you can choose to continue the compilation. And if you do, it'll go into after expansion, which happens after the macro expansion, and the same thing is possible. And there's one more point that you can enter after analysis.
Sorry,
so,
could you explain queries a little bit really quick? You may have mentioned that before, but maybe I didn't catch it.
The queries are a system that's inside the Rust compiler to try and get information from different points. I think for the context of this call, for this presentation, all we need to know is if we give a query that says, can I look at the typing context? That's something that exists, and the typing context is the thing that has all of the intermediate representation. So I'll show the way that you craft that query, and then you can take the typing context and do some manipulations on it. There's more stuff that you can do with queries. They are, as the name suggests, a way of feeding things through the Rust compiler at particular points that you might be interested in looking at here.
Cool, thanks.
So there's 3 points that we can interrupt the analysis and interrupt the compiler to do some analysis. And if we go back to the diagram that I have here, after create root parsing is happening after we've done the lexing and parsing. So we've just created our initial abstract syntax tree. The macros are still unexpanded. And then we have our second query after expansion, which happens after the macro expansion and name resolution. So this is essentially happening on the abstract syntax tree. So no analysis at this point has happened because our first bit of analysis happens when we turn it into here. And our last bit of analysis happens after we get all the way down into the mir. So our third callback is after analysis. So we can have a look after we've done all of that. So we would be expecting that at these points, the type checking and the trait solving, all of that stuff isn't happening. And like if we have a program that is breaking the borrow checker, for example, we would still be able to analyze what that abstract syntax tree looks like. Like it would still be able to craft one and we can still examine it here. But if we had let it go to the point where it would go to after analysis, we would expect that the borrow checker would throw an error. And that's actually what I'll do for the example is we'll have a look at that. So so here I have expanded the struct that I had my callbacks. The impl that I had before was just an empty block. If you remember, it did nothing. It was just like that. But now I've added in some. These are admittedly pretty empty callback functions, but I have all 3 here. There's after the create root parsing, I'm still going to continue the compilation. I do have the ability to stop it. You can change this to stop and it won't keep going, which means it won't create a binary here. But what I've done for this example is I've just shown you can add your own custom code at these points. This is just for the sake of example. All it does is just prints out what phase I'm in. And if I build, just to be explicit again, if I build, nothing happens because it's just building. It doesn't need to take an argument. It got upset at me. But it doesn't create anything, but it's when I run it that it runs the compiler for the second time. And I'm expecting that in the running of that compiler, it's going to print out where it is. And so all 3 of these get communicated. If after expansion, I say stop. So maybe before I do that, like we'll notice that because I didn't stop it at all, it created the hello binary, and the hello binary does what the example does there. It says hello RareSkills. But if I delete that and I stop compilation after expansion, then we won't see this after analysis printed. So doing that, it doesn't get to after analysis. Now, to show what I was talking about, where if we haven't done any analysis, that means that Rust programs that we know are actually illegal, we won't get we will still be able to look at their AST and things. They'll still be legal enough to be turned into an abstract syntax tree. So if we let it can be a U32, it can be 5. If we know, so I haven't flagged this as mutable. And so if I try to assign to it again, that's not allowed in Rust. This is outside the scope of the Rust analyzer, so the Rust analyzer isn't able to do the extra bit of work where it usually gives you the red underline. This is, as syntax makes sense, but it's a broken Rust program. It's not allowed. And so if we go to here, if we're stopping the compilation after expansion, then when I try to do this, this is still pointed there. It's not buffing. It's not throwing an error saying, hey, this is like you're breaking the rules. I found that out in the analysis. But it's only stopping here. We're not going into the analysis at all. So it's not creating a binary. If I let that continue, we should see it throw an error. Even if I stop here, it shouldn't get to the point even where it can print this because the analysis should throw. And that's what happens. It straight away realizes that's you need mute if you're going to reassign to a variable. So that's showing that we can inject code and we can look at different forms, and the different points mean that different guarantees have happened to that code. And so we'll look at a bit more of a example where we actually grab the typing context, like I said before, and do something with it, with a query.
So if we wrote something that doesn't even syntactically make sense, then like...
I think if I try to go A equals, and then what's another keyword? If I go A equals function, this should be enough for it to say, I can't do this. I think we won't even see after expansion. I think that won't even be printed. So let's have a look. Oh, no. Yeah, okay, it does actually. That's interesting. I thought that maybe... I thought that there was more checking happening when it was parsing things in, but evidently
what if we change fn to something empty so that it doesn't, because it might be, maybe it's still might be trying to see it as a variable or something.
True. That's a good idea. If semicolon, so that it doesn't read it off the print line, or I could just remove that actually. Let's just do this, A equals and then nothing. So if we run that, still interesting. So it does create an abstract syntax tree. I did think that there was more of a guard here for a well-formed program, but evidently not. It will go ahead.
Sorry, is it possible that it tries to make sense of the rest of the program, which in this case is empty, before presenting you all the errors? Because if you throw at the first arrow, then you're going to have a hard time doing any.
Oh, actually, that is true. There is like a really rich error system going on where it doesn't just hit the first thing and then throw. It tries to collect as much information about your program as possible. So Jos did have a good point there, that it probably has recorded the error, but it's continuing as far as it can with its compilation in case there's more information that it can spit out to you.
Got it. So if we wanted to break it out the after expansion phase, that would be like if we put some macro in there that doesn't exist or something.
That's a good idea. If we do ABCD macro, I wonder if it will expand this. It threw an error after parsing, continued with expansion. So both.
It's interesting that it sees the error before the expansion. I'm guessing that standard error is getting passed through this thing.
So this printing after expansion is, you can think about it as happening, it's the first thing that we're doing after expansion. So this is after expansion, the first line is here. So the analysis of whether things can be expanded is indeed happening before printing this line.
Got it.
Yeah.
But the error is, but this error thing that's printing out here, that's getting just streamed from the compiler through.
Yeah, this apparently
Or
is not delayed. It just goes through straight away, unless it's racy, but I don't think it would be racy.
Okay, cool. Thank you.
Yeah. So yeah, we'll have a look at something a little more juicy. I think I can go git switch 7. Okay, so now here, what I've done is I've added in a few more crates to be able to look at a bit more stuff. And I've got rid of the after parsing and after expansion callbacks, and we're just looking at after analysis. And so looking back to the graph, I'm in at this point here. We've all the borrow checker, everything's fired. We have our maximum guarantees, I guess, that we can get out of the compiler. And this is the construct with the query to be able to look at the typing context. So there is a function for the query saying, give me the global context. You unwrap it, you get a mutable reference to it, and then you use the function enter, and enter takes a closure. And that closure gives you a handle to the lambda variable, which is the typing context here. And through the typing context, you can call tons of the internal Rustc functions. There's many functions at many different stages that take a tyctx, which I'll show. I'll go over and show you what that is. And you can do a lot of things with this. Any function that takes one, you now have the ability to call. So here, just for the example, I have used the span crate to grab the def ID of the local crate, like the crate that the crate of whatever program we're pointing the internal compiler at. It's going to grab that crate number, and then from the typing context, I've said, give me the name of what that crate is, turn it into a string, and then I get the crate ID again. Could have just saved into a variable, but I got it again. And I'm going to print both of those out. So this is stuff that you normally don't really see at all that's inside the internals, but using the TCX, you can have a look at this stuff. So I can see that the name, we pointed it at this hello.rs program, and also why a binary didn't get built, as I told it, don't build one at the end, just stop. So I can see the name of the crate and I can see the crate number. And since there's only one crate here with printing out this string, it's 0 indexed. And so it being 0 makes sense. So we might have a lot of, depending on what you want to do inside the compiler, you would probably be motivated to look at some particular thing. For just an example, I thought about how if you use Rustc, one of the examples that I gave last week was the CLI command that you can do -z unprettymer, and it will print out. So after piping through, looking at all these CLI args, it's going to do a pretty printing of the program that you pointed at. So here, if I run that command that's from the CLI, I can see this is the mir of the Hello World program. So it's got our warning at the top that we see, and the basic blocks, and it's got a bit of the promoted thing here. But another thing that we can do is, this is just the example that I chose, but inside the Rust crates, there is the very function that does that, and all it takes to do it is a handle to the typing context. So inside here, there's a pretty. And if you have a look for write me a pretty, this is going to print out a human readable representation of the mirror. And so what it takes as an argument here is a TYCTX. And that's what this query system is giving us. So any function that's in here, I think, we should be able to call, and we can do our own manipulations or our own, we can use what's available in the Rust compiler to look at what we want. So maybe for the sake of this example, we're going to just call that directly. At least that's what I thought of as an idea. And so we can bring that function in. So here it's not able to route to it because I haven't brought it in. But if I use the Rustc middle mir write mir pretty, bring that function in, all it needs is access to a TYCTX, which we are given by using this setup. And if I do the cargo run and point it at it, so first it should print out the crate number, hello, the crate name and number, and then it does indeed call that internal function that we saw before. So this is showing how we have some amount of ability to sort of control and craft what we're calling. I saw that this prints out a promoted. So we can see here that this constant is a constant that gets promoted, which maybe is a little bit out of scope of the discussion here. But another thing that I thought to do is maybe it would be interesting to be like, well, I want to know what a promoted looks like. Like, what is this? And so what I did to discover what that would look like is I went into the Rust compiler and I grepped for like functions that had the word promoted, and I found this one here, promoted mir, and it takes a TYCTX. And so I thought, well, it needs a def ID. And so in the previous rounds of analysis, I know that there's a in the here, everything that has a body gets a def ID. So from the typing context, I'll grab all of the here, I'll get all of the body owners, and I'll iterate through them. And if they have a promoted, I'll first print out its size. We can see from here that there should only be one. That's all we're expecting. But I'll print out all these promoteds and I'll have a look, like what are they for every P that's in there? Let's print it out and have a look at what that is. And running that, okay, it gives us a warning there, but it spits out a whole bunch of the internal representation of like, what is this promoted thing? So the version that we saw further up here, this is like a pretty printed version, whereas this is just dumping out kind of the struct of what it is. So that was just some way that getting this representation, I don't think you can do this from the command line, but you are able to do it and much more by interacting with these callbacks. And that's sort of the point that I was hoping to demonstrate here.
What's the length mean in here? Which site, the promoted.len? What's it measure?
Yeah, so there might be multiple things promoted. So this gives you a vector of promoted things. Now, we can see here that inside promoted, there's 0, and that's the only thing that gets pretty printed. So there's just one thing in this promoted. But I did the length to it. I just wanted to see, is there, for this example, I'm expecting there to be one thing, and there was indeed, there was just one thing. So that's why that was there. Cool. So this ends up being handy for us at Runtime Verification. We use this setup to do some analysis. So this in a an environment where this would actually come in handy, aside from just poking around and looking at some things. We have a project where we want to get out all of this intermediate representation called the stable mir, and we wanted a JSON serialized version of it, and that didn't exist. So we used this paradigm where we took some args, same thing, and then we call this function, which is a stable mir driver, which is from driver. So I'll go and show that in a second. And we pointed at this function here called emit smear, which comes from the printer directory. Oops. And so that driver is doing the same thing that I did in that example. We have a callbacks. This callbacks, in this case, it takes a function, which ends up being that emit smear function that I described. And it does the same thing. It grabs the queries, says, give me a global context. With there, I want to enter. Give me a closure. The lambda argument is going to be the typing context. And then it says, I'm going to run that callback function. So in our case, it's the emit smear function. And so we use the Rustc driver and give it the arguments and give it the callbacks, which we've created here. So why we want to do that, like I said, is we want to do some serialization. And the serialization that we need, we have some problems because it's not in a form that's ready for serialization. So here is the emit smear function. Both branches here call emit smear internal. And this is a big block of code that we're not going to dive into, but here's where we do all of the serialization to JSON. And so that was the whole goal of this project, is we want to serialize this stuff as JSON. But what we had to do first is we had to do some like normalizing of the form. We had to do the monomorphization ourselves. And so being able to carry around this typing context and do all of the things we needed allowed us to get this mir in the form where we were able to serialize it. So there's a like industry level use case for where this sort of stuff comes in handy. And once we have that serialized version of this stuff, this is input to another program that we write, a tool that we're building. So that's the motivation for why we do that. Cool, Codegen Backend. So at this point, we've been interacting with the IRs at this level, but you do have the ability to let all this be, let it go through, and replace the Codegen with something that is more what you need for your use case. Inside the Rust compiler, you get three for free, I guess. There's LLVM, the default one, GCC, and crane lift. But you aren't limited to just using these. In fact, if you write your own, all you have to do is implement this trait, CodegenBackend, and call the Rustc driver function, set make CodegenBackend, and point it to something that successfully extends this. And you can have your own custom code generation. I'll show just briefly what those traits look like. So the CodegenBackend trait that you need to extend, it's quite beefy. There's quite a lot of stuff that you need to put in here, but that makes sense because you need to tell Rust how to generate all the code from the IR. Sorry, go ahead.
So if we were like compiling Rust to some custom blockchain which has its own VM, this is the part we would override. It has its own instruction set.
I think it is. Well, I guess you could do that. Yeah, that is something that you could do. I'm not aware of anyone that uses this in the blockchain space, although that doesn't by any means mean that it's not used there. But yeah, if you wanted to do that, this would absolutely be a way that you could do it. You could create your own Codegen backend and call this function pointing at it, and it would spit out the assembly of your definition according to the extensions of the trait that you defined. Yeah, so that is possible.
Okay, I think somebody just asked a similar question. Are the Rustc _driver callbacks used to generate a solidity verifier .sol for a Halo 2 proof?
I don't believe so. I don't know. There is I'm not sure if anyone is consuming mere from a stream like that. And I would think that if you were to do it, you would need to do it after analysis. And the reason why I'm not sure if people are consuming mere like that is there wasn't really a serialization for it that we came across. And so we had to do that. And so what that means is no one was using it in a portable sense. I suppose if these people were doing this Halo 2 in the Rust environment, because you can then just access the stuff directly and write your Rust program to do whatever, that might be possible. Yeah, I can't give a concrete answer for that. But if what you needed for that was to look at the IR, then yeah, you could hook up to it. Or another way you might do it, it might be through this Codegen backend. So this project that I mentioned here, Carney, I think they use this sort of paradigm to be able to transfer things into what they need for CBMC, but to do bounded model checking. I don't think we have the time to go into Carney, but I would encourage anyone that was interested to look for this trait being overwritten and this function being called inside there to see what they're doing with that in a real world program.
Okay, I just got confirmation to answer the question. Thank you.
Nice. Okay, building Rustc. So this is where I'm going to point out some things. So if you're using Rustc, this is just a clone for it. How am I doing for time? Yeah, okay. If you're using Rustc, there's every chance that the way that the compiler is will make it hard for you to, and I'm saying it's like if you've got this downloaded like I have and you've decided I'm going to change things, I'm going to hack away, I'm going to do it for fun and profit. There's a couple of tricks that you can do to make that a lot easier for what you need. So the first thing that I'll say is there's a couple of build scripts. I'm going to get the compiler building, and then while it's building, I'll explain what they are, because the first pass is a little bit slow. So if we call this x.py, which x and x.py are the build scripts, and we say that we want to do it with, what is it? It's setup. It's going to download a few other things, and then it's going to give us 5 options, and it says, here are some profiles. Which one are you interested in? And one of them is compiler. And since this is about like maybe we want to hack away at the Rust compiler, then choosing that one has a bunch of configurations set up so that our life is much easier in doing that. So just give it a tiny bit and we'll go through. So it's asking us, what would we like to do? There's A, B, C, D, E. We're going to choose B. We would like to work on the compiler. It asks us some things like, do you want hooks? What are we using? We're using VS Code. And no, we don't need to worry about that. Cool. And so now the compiler is set up for us to do programming on it. I'll explain the compiler thing in just a sec, but let's first get things building. So if we do time.x build, this is just building the Rust compiler raw. And so we'll time it and see how long that takes. So that's working away in the background. Now, what exactly are you signing up for when you choose the compiler configuration? You can see in this file here, config.example.toml, a whole bunch of different settings. And this is a big file because there's a whole ways that you can customize this compiler. Now, what's happened when I've chosen the compiler profile is it's taken out a series of these and it's set them to a configuration and saved them in this config.toml. Okay, sorry, it just points to the profile for the compiler, but this pointed to file has a bunch of configurations, a bunch of settings that are here that are going to be useful for us. So there's a whole bunch of different stuff, general build configurations, and this file is great for explaining everything that's in here. But obviously, it's a bit too much for a newcomer to know, what do I want to turn on and off? So what the Rust compiler team did is inside source and bootstrap, there is defaults, and they have a few default settings that you would be interested in. And so when this config.toml is pointing at this profile compiler, it's pointing at this here, which, as you can see, these are uncommented. This is the setup that it thinks is best if you want to build the compiler and you're changing things and working on it. So that's already one thing that's really nice, is we have things like debugging is on in the correct version that's going to be useful for us. Incremental compilation is enabled. And you can read through and have a look at what's in here in particular. So we're still building here, but this is maybe where I'll point out what exactly it is that's building. Once we start the build, there is this build directory. And in here, under the name of our target, so this machine that I'm on is a x86 Linux machine. So my target is this one here, the only one here. And in here, maybe I should have shown this earlier, but what it's been progressively doing is it's building a stage 0 compiler. It's building stage 0 Rustc, the standard library, and then it starts moving on to the stage 1 compiler. So if you remember from the last talk, I mentioned that Rust is bootstrapped. Rust is built in Rust itself. This stage 0 compiler is like a small subset of the language that ends up building this bigger version of the compiler, stage 1 compiler. And then I think when anything is going to be actually published out there, like a binary for you to download from GitHub and use Rustc with, or something through Rustup, this stage 1 compiler tries to build itself again, and the result of that is the stage 2 compiler. And I think that's just for extra safety, like that, that this should be able to build itself identically. Now, everything that I'm explaining here is available, and I would encourage people to look at it in the Rustc dev guide. Pretty much everything I've explained in all this talk is just a filtered down interactive version of the Rustc dev guide. So in how to build the compiler and run it, there's also a suggested workflows. So that all of that stuff about doing the profiles and stuff was in that first bit, but there's a bit more that you can do to even make things faster, and that's using keep stage. And so that's what I'm going to explain next. So if we save, so our first run here, our first run here went at this time, that's not really the kind of time that you'd like to have for compilation if you're working on something. This machine's multi-threaded, and so 28 minutes of user time went down to 3 minutes. But even so, if you make a change to something in here and then you want to compile and see what happened to your change, that's not really acceptable. By 3 minutes, you've already opened Instagram and you're lost to the void. But let's choose something to change. We'll choose, I should change that. Yeah, I'll change that function actually that dumps the mirror. So that's in pretty. So let's get rid of that. I think it's called function right near pretty. That's it. And so we're going to make some changes to this. So here's where it writes the line. Okay, actually, I'm just going to grab that. So we're going to do that again. But now let's, what do we want to say? We want to say, oops, what am I doing? I guess, hello, this is an example. Cool. So now I've made a change to the Rust compiler. The documentation here tells me that, and I saw in the build here, that a stage 1 compiler, okay, it doesn't want to show me, but a stage 1 compiler existed for my target. I've only changed one minor thing here. I don't actually have to build the entire compiler again. And I can tell it not to do that by saying, what did I do before? I did .x build, and I want to tell it, so keep stage 1. And so what it's going to do is incremental compilation, and it's going to try and keep everything from stage 1 that it doesn't have to change. And so we'll see how fast does it build it with this in mind. And so here, all of these Rustc underscore blah, 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 is it building the crates that it must build to accommodate for the change that I put on this line here. And it shouldn't change anything else, although it will rebuild the standard library. But this time now is much better than what we had before. So if we go to here, now we have real time of 21 seconds and only a minute and 20 seconds of user time. So this is pretty good. Like 20 seconds isn't too bad a wait for building an extremely complicated compiler. It can be a little better, but what I'll show is that we have actually changed the binary at this point. And so by doing that, what I need to do is go inside the build directory under my target, which if you remember was the x86 Linux one. There should be the stage 1 compiler. And in here, there should be a binary, and there should be Rustc, because that's the whole thing. We're building Rustc. And if I'm going to have to give the file. Is there one? Just, no, there's, okay, that was crazy. This hello.rs. Oh yeah, here we go. And so function main. I need to give it a Rust program to point at. Cool. Whoops. So there is a function, sorry, there is a program to point the Rust compiler at, which is hello.rs. And we're expecting it to compile it, and it should have a binary there. And if I need to make sure that I call this here. So what I need to do is the -z unpretty equals mir, and it should spit out on the command line here. Yep, and it's got our change. Our change is in there. So we've now made a change to the Rust compiler, and admittedly all it is a printing change, but I mean, you can do whatever change you want. You could make addition, subtraction, and subtraction, addition, or something like that. And this is like a pretty reasonable turnaround time. Now, the last thing that I'll show is you can actually kick this time up a little bit more. So let's change this text so it has a diff for something to make the difference with. And come on, W, yep. So I need to build this. So I want to do keep stage 1, but if you actually tell it, I don't fully get this, but if you point it at the library, you say build the library, because you can put arguments in here. Like you could do that without the keep stage 1. But if you do that and tell it to keep stage 1, one pass that it was doing before, what did I do wrong? Building the bootstrap. Oh. Sorry, this is SSH, so maybe it just got a little bit hairy. Yeah, okay. I think that the text that it was showing me was not actually what it was on the server. But here it's building it again, and we'll have a look at what time. I don't really know why when you add the library, see, it didn't build the library here. If we go all the way back up, back here, you can see that it started building, oh no, it started building Rustc. Oh, I think I get it. So Rustc must happen after the library. But here we're telling it just build up until the library, and then we're saying keep stage 1. Okay, I get it. And so this time is much faster. So if we have a look here, we're now down to 36 seconds of user time, but it actually took 13 seconds to make that change. Now we can kind of hack on the Rust compiler, and we're not going to get interrupted in our flow of ideas as we start changing things. Yeah, I think that's everything that I have to say, actually. I think I'm done, which it looks like it's not a bad time to be done. So yeah, I'm up to questions.
Really nice, thank you.
Sweet. Cool.
What are the most common backends that get swapped out if it's not one of those 3 that are included?
The most common backends that get swapped out are definitely going to be between CraneLift, GCC, and LLVM. But aside from that, as I mentioned, like Amazon, I think it's Amazon that does Carney. It might actually be a third-party org, or at least Amazon's really tied with it. But you know, they have their own reason for they want to do this bounded model checker, and so they have that. And then there's projects like Aeneas and Charon, and so they do a similar thing. They exchange the Codegen backend to try and point to the different interactive theorem provers that they're working with. I'm sure that there's more. I have those examples off the top of my head because I'm from the formal methods world, and those are formal methods projects that do this. Any queries namespaced? Oh, our queries namespace. So those are already, these queries are already existing inside the Rust compiler. And so you have a really limited option of what you are. So in that sense, they are namespaces in there, already predetermined. They grab the typing context from where it is in the analysis that, in the callback that you've got it. Trying to think, what do you mean exactly by namespace? Like at that point, there shouldn't be any problems with like the resolution of any names. Like as in, I don't think that you should be able to call a function by the name of a query and it be confused when you're using the query system. It's like, hang on, which function do you want? Because it will be fully elaborated by that point. Oh, are they across different layers? Yeah, I mean, you could think of that in the sense of there's different IRs that still through the process of the compiler happening, they're still there and accessible to you. I showed that with the example where what I had was I was looking at the mirror, but I was looking at the promoted stuff that was in the mirror, but actually I wanted to grab all the def IDs, and all the def IDs happen in here. So I said, okay, well, we've already processed all of our here. It's just sitting there. Give me that. Let me see all the def IDs. And then from that, I'll use some mirror query, some functions on the mirror that take a def ID. Are there any compiler vulnerabilities were discovered from doing Yeah, absolutely. Yeah. So there's you know, if you go to the Rustc GitHub, there's a issues board there. So the compiler does have bugs. Nearly all compilers have bugs. They're just hard to find. The Solidity compiler has bugs. It has previously in history had bugs. I think the Viper compiler as well, because I think a lot of people here are more familiar with like EVM world. These are an inevitability in complicated software, and the Rust compiler itself has historically had some bugs that it needed cleaned up, and there's still ones there. So when the compiler itself errors, that's called an ICE, an internal compiler error. And generally, if you're doing something and you get an error, which is it's clearly not a normal error. It's going to have crazy symbols, all this stuff going on, dump like a ton of information. And if you start reading through that information, you might be able to detect, you're like, oh, wow, this is like an internal error. This isn't anything to do with my project. This is like internal to the compiler. It's gone haywire. Usually that stuff, you want to go to the compiler GitHub, go to the issue board and, you know, say the conditions that your ICE occurred in, and then they can patch the bug. Really, the only way to avoid bugs in compilers is to, well, I guess you could try to formally verify them. And there are projects that try to formally verify compilers, but compilers are pretty complicated software. So yes, usually you have to restrict to a subset of the language. You can't fully verify the entire compiler. Like you go, okay, well, we'll, you know, verify C, but C that looks like this kind of thing. It doesn't have these features, maybe. Yeah, making sure that an entire compiler that's as complex as something that can build an entire operating system is free of bugs is a pretty big challenge.